Alright, so welcome to Math341, Lecture 18. Today we're going to do a little bit more on the gamma function. We're going to do chi-squared random variables. We're going to see an application to do volumes and surface areas of n-dimensional spheres. And we're going to see what you get when you have sums of chi-squared random variables. So this was a little bit of a fast-paced class the last time I taught this. I've deliberately moved a little bit of the material to some of the lectures earlier in the semester. I want to start off with a dimensional analysis proof of Pythagoras. So by dimensional analysis. And in case I haven't remarked it already, who is the one US president who is credited with a proof of the Pythagorean theorem? Garfield. And how did Garfield die? Coming to Williams for his 25th reunion. Okay, so if any of you ever get elected president, be careful coming back for your 25th reunion. I'm assuming by now that everybody knows the Pythagorean theorem. A squared plus b squared equals c squared. Essentially, the only thing that is debatable is how do you draw your triangle, how do you label your sides. So I'm going to give you a dimensional analysis proof. I claim the area is some function of c and the angle theta. And if you think about it, if you know trigonometry, A is just going to be c cosine theta, B will be c sine theta, and then the area would just be their product times 1/2. It makes sense that you have a formula like this. We could do a little bit better. It's going to be some function of theta times c squared. Because area has to be in meters. If I triple the hypotenuse, I'm going to triple A, I'll triple B, and the area is going to go up by a factor of 9. So all I'm really using is, I know the area of a rectangle is length times width, so the area of a right triangle will just be 1/2 that. So we know the area has to be of the form g of theta with g sub undetermined function times c squared. Okay? How many of you remember your geometry classes from all those years ago? The big thing is to draw an auxiliary line. We want to draw an auxiliary line. Anybody have an idea of what line we should draw? Any thoughts? Well, we're trying to prove the Pythagorean theorem, so what kind of triangles do we like? Right triangles. Can you give me any way to draw a line and create more right triangles? Yeah. Where do I come from? Yeah, from the right angle. So if I come over here, I'm going to give these triangles really crappy names, triangle 1 and triangle 2. If this is theta, and this is 90, this is 90 minus theta over here, which makes this angle over here. So they're similar triangles. And so I have the area of triangle 1 plus the area of triangle 2 is the area of the big triangle. Okay? Well, we just realized that the area of a right triangle with hypotenuse c and angle theta is g of theta c squared. What's the area of triangle 1? A squared times g of theta. So we get g of theta times a squared. For this one, we'll get g of theta times b squared, because b is the hypotenuse here, is g of theta times c squared. So now what do we do?
G of theta is just a number, right?
G of theta is just a number.
We just divide through.
Right? But since we are in a math stat class, before we divide by a number, what do? We check and make sure it's not 0. Well, if g of theta was 0, then that would mean the area would be 0. That's absurd. So now we can divide by g of theta, and we get a squared plus b squared is c squared. So this is a dimensional analysis proof that gives you some idea of why Pythagoras is working. Okay. And this is going to be useful later today when we start talking about finding the volume for the n-dimensional sphere or the surface area. We are going to do change of variables without actually writing down what the change of variables are. Okay? So I'm going to recall a couple of facts that I will just leave on the board for the rest of today. So we have the gamma function is equal to the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. We have gamma of s plus 1 is s gamma of s. We have the cosecant identity, which says gamma of s minus 1 is pi over sine pi s. If x is normal 0, 1, then the expected value of x to the 2m was equal to, I want to make sure I get my constants right, 2 to the m divided by square root of pi gamma of m plus 1. Right. So here are a couple of useful identities. Right. So here's a couple of useful identities. The only one we haven't done is the cosecant identity. And so there are proofs of this in the book. I'm not going to go through and prove this now. You have to be careful. Your instinct should be to prove this. Well, I have an integral representation of the gamma function. Let me do it twice. And maybe for this one I use the variable x, and for this one I use the variable y. You have to be careful. To use this integral, we need, say, 0 less than or equal to s. We need s to be a positive number. Over here, I need s to be positive here, and then I need, oops, that's a bad typo. It's right, 1 minus s. I need s to be greater than 0, and I need 1 minus s to be greater than 0. So this, I need 0 less than s less than 1. So I can only prove this initially when 0 less than s less than 1, but then we can extend it to all values of s. Right, there are ways to do this. You learn this in a complex analysis class. We really only will need this for s between 0 and 1. Anybody have an idea of what the most important value of s is going to be? So when you look at this, what value of s is screaming to you? Please, please, please use me. 1/2. Because if you take 1/2, then s and 1 minus s are the same. And then you get at s equals 1/2, that gives you gamma of 1/2 squared is going to be pi over the sine of pi halves. Well, the sine of pi halves is just 1. So this then gives you that gamma of 1/2 is the square root of pi. This is the normalization constant for the Gaussian. This is an extremely important quantity to be looking at. Okay, so again, I'm not going to go through and prove that. It can be done elementarily. Since we proved the area of the Gaussian is 1, we actually know that gamma of 1/2 equals the square root of pi from this. Just take m equals 0. And so if you take m equals 0, then you get gamma, this should be, I think, m plus 1/2. 2 typos, that's terrible. All right. So we know that when m equals 0, this equals 1. So we get 2 to the 0 over square root of pi times gamma of 1/2 is 1. That gives us gamma of 1/2 is square root of pi. So because we proved that the normalization factor of the standard normal is 1 over square root of 2 pi, we actually know gamma of 1/2 elementarily. We had to go to polar coordinates, but we still have that fact. All right. So we are going to be using these results a little bit. What I want to do now is I want to introduce the chi-squared distribution. So we'll say x chi-squared random variables. X is going to be chi-squared with new degrees of freedom. So nu is going to be our parameter. So the normal has the parameters mu and sigma squared. The exponential has the parameter lambda. The chi-squared has the parameter mu. And it's going to have density function, which is going to be 2 to the nu halves gamma to the new halves to the negative 1, x to the new halves minus 1, e to the negative x halves, if x is greater than or equal to 0, and 0 otherwise. Given that I have had 2 typos already, I will double check and make sure that I don't have 3 good. Okay, so this one I actually did do correctly. So, I'm saying that this is a probability distribution. What do you want to check? PDF. Okay, what do you want to check about the PDF? What's equal to 1? Not the PDF. Okay, so 1, show integral is 1. Exercise. And the other one? Non-negative. And that's just inspection. So the non-negative isn't so bad. To integrate this, well, I've got a gamma of new halves. Gamma of s, recall, is the integral from 0 to infinity of e to the negative u, u to the s minus 1 du. I'm just using a different dummy variable. You can see this looks a lot like what I will get when I integrate this from 0 to infinity. The annoying thing is I have an x over 2. In the definition of the gamma factor, the gamma function, I have a e to the negative u. So this suggests the change of variables u equals x halves. Or, if you like to look at it the other way, x equals 2u. And if you go through and you do the change of variables, I'll leave you the calculus, you will end up showing that this integrates to 1. You can say, oh yeah, this is kind of looking like s equals new halves, that's why I have this here. And because I have this factor of 2, that's probably where this 2 to the new halves comes from. So at this point, you should be a little bit pissed that the definition of the chi-squared random variable has an x over 2. Right? Why would we do this? Any thoughts? It must make other things better. Right? Tanstoffel, there ain't no such thing as a free lunch. By having the slightly worse definition here, it should hopefully help us with some other algebra later in the day. And that's where we're going to really get the dividends, is it's going to help us when we try to look at sums of chi-squared random variables. So we have a lot of things to do. So the first theorem, if x is normal 0, 1, then x squared is a chi-squared with 1 degree of freedom. So if you've taken stats, you've seen squaring errors. If you haven't taken stats classes, we will see that later when we get to the method of least squares. If the errors are normally distributed, then when you square them, that tells you each of these errors is like a chi-squared distribution. Well, this is only the case if it's a normal mean 0 variance 1. Otherwise, you have to play some small games. Not a big deal. So let's prove this first. All right, so let's let y equal x squared. So the cumulative distribution function of y is the probability that y is less than or equal to little y, which is the probability that x squared is less than or equal to y. How can I interpret x squared less than or equal to y? Okay, and what do I get?
So x is greater than or equal to minus.
Good. So the probability negative square root of y less than or equal to x less than or equal to the positive square root of y. Because x is not non-negative, I do have to be very careful about this. And now, this is where you need to remember to be lazy. Our end objective is to calculate the PDF. This is calculating the CDF. What am I going to do to the CDF? I'm going to take the derivative. So over here, I can write this as the cumulative distribution function of x at the square root of y minus the cumulative distribution function of x at negative square root of y. I don't have to write down what this is because this is not going to last long. the very next line we're going to take its derivative. And we'll get the PDF of y is equal to the derivative of this, which becomes a small f at square root of y, times the derivative of square root of y, minus at negative square root of y times the derivative of square root of y. All right, well, the derivative of square root of y is 1/2 y to the minus a half. The minus and the minus will be enforced. We'll get a 2. So we get a 1/2 comes down, which cancels with the 2, I think. And I think we get the cumulative distribution function, so the PDF at square root of y times y to the minus a half. So this is then going to be 1 over square root of 2 pi e to the negative square root of y squared over 2 times y to the minus a half. And I'm going to write y, how should I write y to the minus a half? It is y to the minus a half, but if you look at everything, we always have minus 1. So I write it as y to the half minus 1. And now when you look and the dust settles, this, let's see. I get a 1/2 y to the minus a half, and then I get another 1/2. So the two 1/2s reinforce. And so if you look at square root of 2 pi, have I made a mistake? Unless this is supposed to be negative u halves. So maybe that's supposed to be a negative 1/2 over here. Yes, it's supposed to be negative 1/2 there. Okay, good. So this works out perfectly. So I've got the 2 to the negative 1/2. I know gamma of a half is square root of pi. That's this piece over here. X to the new half's minus 1. So this is pi square with mu equals 1. And that finishes the proof. So this shows that if we have a normal random variable and we square it, we get a chi-squared random variable with 1 degree of freedom. Okay. Any questions about this? So now what we want to do is we want to move on to, well, what if we had more random variables? And so the first thing we can do is we can add sums of normal random variables. But we already know how to do that. But these are going to be now sums of squares of normal random variables. All right. Is everybody done copying through here? I want to try to keep as much on the board as I can. So the first theorem we've now proven. The second theorem if xi is normal 0, 1, then x1 squared plus xn squared is chi-squared with n degrees of freedom. And in the last theorem, if yi is chi-squared with nu I degrees of freedom, then y1 plus yn is chi-squared nu 1 plus nu n. So when we look at this, we really don't need the second theorem. The second theorem is actually a special case of the third theorem. We will prove the second theorem just by itself because it will give us a nice result. It will give us formulas for the n-dimensional sphere. Out of curiosity, how many people have seen the formulas for the volume of the n sphere? Okay, so I'm not seeing huge numbers of hands going up. It's something that's worth knowing. Now, let's talk about proving theorem 3. We want to show that the sum of chi-squared random variables is a chi-squared where the parameter is the sum of the n's. It's the sum of the degrees of freedom. I claim it's enough to do just n equals 2. Why is it enough to do just n equals 2? Yeah, we can go. This is one of the key techniques we have. We have y1 plus y2 plus y3 plus y4 plus yn. We first group these two together, and now this gives you a new chi-squared random variable, y12, where this is a chi-squared random variable with nu1 plus nu2 degrees of freedom. And then we group y1 plus y1, y2 with y3, and we get y123, which will be chi-squared with nu1 plus nu2 plus nu3. So it's sufficient to prove this in this special case when nu1 equals nu2. I'm sorry, when n equals 2, and we just have two terms. Right. It's not enough to do it just the special case when n equals 1. There's nothing to prove there. But if we can do the case of 2 by grouping by parentheses, we're done. All right. So let's prove it in the special case when n equals 2. So now, proof, and this is n equals 2. So we want to calculate the density of y1 plus y2. Any thoughts on what technique we should use? How do we get the density of a sum of two things? Did you want to try in the back?
Oh,
No.
convolution.
Convolution. So if we call this maybe y, then the density of y at y is going to be fy1 convolved with fy2 at the point y. So this would be the integral t goes from minus infinity to infinity of fy1 of t, fy2 of y minus t dt. And now we have to start doing that integration. All right, well, when we do this integration, we know the chi-squared random variables are non-negative. So where should t start? It should start at 0. So this one over here forces t to be greater than or equal to 0. What about this? What does that force on t? Less than or equal to y. Because I can't have y minus t be negative. So I now reduce to the integral t goes from 0 to y of fy1 of t, fy2 of y minus t dt. You might be a little concerned now that we have, unfortunately, y both in the integrand and in the boundary term. Oh well. Now, our goal is not to evaluate this integral perfectly. It's very important to remember what the objective is for today. What is our objective? It's close to evaluating the integral, but I don't need to evaluate the integral completely. What can I be off by? By some constant. What do we know this has to integrate to? 1. It is the PDF of a probability distribution. We know this must integrate to 1. It has to integrate to 1. So if we can just figure out the functional dependence on y, we win. because then the normalization constant will come. And we have an intuition as to what it should be. I've told you sums of chi-squared random variables is chi-squared. This is one of the reasons why I have this here. You know, well, if we could prove that result over here, that would give us some intuition for this more general case. So all we have to do is evaluate this integral enough to figure out how it depends on y. And then we'll get the normalization constant for free. All right. I will try to keep that little fact up. I'm not sure how long we'll be able to survive. All right. Okay. So now let's do the calculation. All right? And again, we are only trying to calculate it enough to detect the y dependence. So we get fy of y is the integral from 0 to y. And now let's substitute. So the first thing is I've got to substitute for this density, right? I don't want to keep writing 2 negative nu over 2 gamma nu over 2. I'm going to just say there's some constant c1 from the first one. And there's going to be some constant c2 from the second one. All that I really care about is the functional dependence. So I get x to the nu halves minus 1, e to the negative x halves. Okay, so for the first one, when I put in t, I'll get t to the nu 1 over 2 minus 1, e to the negative t over 2. And then the second one, I'm going to get y minus t times to the power of nu 2 minus 1. And then I'm going to have e to the negative y minus t over 2. So this is going to be c1, c2. And now notice, look, we'll have a e to the negative t halves and an e to the positive t halves. Yes?
Where does C1, C2
They're just the normalization constant. The 2 to the negative nu halves, gamma nu halves inverse.
Okay.
You know, it's just some constant. Yes?
The rest is blocked out.
I'm sorry?
The rest is
Okay. Is there any tall person who wants extra credit? We'll just wait for a moment. So we're just substituting in over here. All right. So when the algebra settles, we see what's really nice is the e to the negative t halves cancels with the e to the t halves. We are left with an e to the negative y over 2, which we can pull out. So you get e to the negative y over 2. And now we have the integral from 0 to y, and I'll write t to minus it's a t integral. And we have t to the nu 1 over 2 minus 1, y minus t to the nu 2 over 2 minus 1 dt. All I need to do is sniff out the y dependence. I think it's a chi-squared. This is looking like a chi-squared. That's good. This is only depending on t. This depends on y and t. So what I want to do is I want to change variables. I want things to be equal. This part has a y dependence, this part doesn't. If I could somehow give this some y dependence, I could maybe pull the y outside the integration. What should I change t to? It's going to be something involving y, so let's let t equal u times y. And now dt is going to be y du. T goes from 0 to 1, u goes from what to what? Oh, so t goes from 0 to y. What does u go from?
0 to y squared.
Not 0 to y squared. If it's y squared, I would read 0 to 1. Now my bounds of integration will be independent of y. And so we get that this is c1, c2, e to the negative y halves, integral u goes from 0 to 1, t to the nu halves minus 1. All right, t is yu, so we're going to get y to the nu 1 over 2 minus 1, then u to the nu 1 over 2 minus 1. This part over here, t is y times u, I can pull out a y, so I'll get a y to the new 2 over 2 minus 1, and then I'll have 1 minus u to the new over 2 minus 1, and then dt becomes y du. All right? So you get c1, c2, e to the negative y halves. Then here I'm going to get a y to the new halves minus 1 plus new 2 over 2 minus 1 plus 1. So I'm going to get y to the new 1 plus new 2 over 2 minus 1. All life is good. And then integral of the nightmare. U goes from 0 to 1 of u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. That's just some constant. It has no y dependence. So I get c1, c2 times c, y to the new 1 plus new 2 over 2 minus 1, e to the minus y halves. And so this has to be the normalization constant of a chi-squared random variable. There's nothing else it can be, because it has the same functional dependence. So when I integrate this, I get the normalization constant of a chi-squared random variable with new 1 plus new 2 degrees of freedom. Okay. So this now proves the special case of the third theorem when n equals 2, and now by grouping we have it in general. Okay. This is the key idea, is trying to change your variables in such a way that you can exploit what's going on without having to do the calculation. You can't evaluate this integral directly. It's not fun. For those of you who've taken stats, what is this related to? What distribution? Beta. So this is related to a beta distribution. It's related to products of gamma factors divided by gamma factors. You can do it. It's wonderful. It occurs in a lot of things. But isn't it nice to just bypass that and integrate without integrating? Yes. All right. Any questions on this? All right. Let's go up a level now. All right. So we've proved theorem 3. Let's prove theorem 2. It's unfortunately not quite enough to do theorem 2 just in the case n equals 2 and then do grouping. Because if we try to do n equals 2 and do grouping, well, unfortunately, the sum of the squares of the first two is going to be a normal random variable with a variance of 2. And that's not going to be exactly the same over here. So we really do need to prove this in general. If people want to, I'm happy to do the case n equals 2 just as a warm-up, or we can just jump into the general case. What do people want to do?
Jump in.
Jump in, aye. So again, first loud voice wins. If you are upset with that, be louder and faster. All right? Proof. Let's let x be x1 squared plus xn squared. Out of curiosity, how many of you remember your spherical coordinates? I remember both the mathematician's version and the physicist's versions. I always have to rederive which one is which. I believe the ones I tend to use is the physics ones because I saw them in physics before I saw them in math. How many of you have seen hyperspherical coordinates? So like in n-dimensional space. We need that today. All right. So let's calculate the cumulative distribution function of x. So this is the probability that x is less than or equal to little x. This is the probability x1 squared plus xn squared is less than or equal to little x. Well, when you see a sum of squares less than or equal to x, what shape do you think of? What? A sphere, an n-dimensional sphere, and what's the radius? Square root of x. So this is a n-dimensional sphere with radius square root of x. And then I will put this in quotes because depending on what book you use, some people would call this an n-dimensional sphere, some people would call it an n plus 1 or an n minus 1, depending on how you want to do it. It's a sphere in n-dimensional space. So if you want n-dimensional space. It's a square in n-dimensional space. All right. So let's calculate this. This is going to be the integral over x1 squared plus xn squared is thus equal to square root of x. And now I put in all the densities. F x1 of x1, f xn of xn, dx1, dxn. All of these are Gaussians, so they're all going to have a 1 over square root of 2 pi. I have n of them, so I get 2 pi to the negative n halves. I then have the integral over x1 squared plus xn squared less equal to square root of x. And then I get an e to the negative x1 squared over 2, e to the negative x2 squared over 2. So this is going to be e to the negative x1 squared plus xn squared over 2 dx1 through dxn. So this is the integral we need to evaluate. It's an n-dimensional integral. When you look at the integrand, what does the integrand depend on? Not much, right? The integrand only depends on the sum of the squares. So what we want to do is we want to use n-dimensional spherical coordinates. Yes?
Where did x go? Like x to the...
It's right over here. The sum of the squares is at most square root of x.
Oh, okay.
So we're calculating the CDF. We're going to calculate the CDF, and then we'll take the derivative at the end of the day.
Oh, what's the upper bound on that integral?
Well, I'm just trying to write this in a concise way in n-dimensional space.
I see. Okay.
Yes. So if you want x1 goes from minus square root of x to square root of x, and then x2 goes from, you don't want to write it down explicitly. Right? This whole lecture is all about integrating without integrating. Okay? If you want, I will meet with you privately and integrate and do all the details. You do not want to do that. I don't want to do that. Okay? We need n-dimensional spherical coordinates. So we're going to have r squared is going to be x1 squared plus xn squared. And then we have angles theta 1 through theta n minus 1. And we need to figure out what the volume element is. And we need to figure out what the ranges of the angles are. Fortunately, dx1 through dxn, I claim, is of the form r to the n minus 1 times some function of the angles dr d theta 1 through d theta n minus 1. That this is the functional form of how the volume element transforms. And this is why I started today's lecture with the Pythagorean theorem, proving it by dimensional analysis. Say, look, we're dealing with areas. Areas are going to be meters squared. The d thetas have no length. Theta is a unitless quantity. So since that's a unitless quantity, we need to somehow get it up to a meters to the n. So each theta has to have an r with it. dr has a meter by itself. That's why you get an r to the n minus 1. If you think back to polar, that's why you get r dr d theta. If you think back to spherical, you have the rho squared d rho, and then I think sine phi d theta. Yes?
Where's the second? Where's like rho?
Well, instead of using rho, I'm using r for the more general case. I am not writing down what this nasty function g is. It's just some function of the angles. All that I need to do is I need to identify how it depends on the radius. What is the volume element? The volume element has to look like the radius to the n minus 1 times something that depends on the angles in a possibly nasty way times the volume element in the generalized spherical coordinate space. Yes?
For the integrating constraint, why is it square root of x if it's the sum
Oh,
of squares?
you're right, sorry. That should be x, thank you. Or square root of x squared. To just really remind myself that it's a circle of radius square root of x. All right, so now we get that the cumulative distribution function of x at x is going to be 2 pi to the negative n halves. We will have the integral r goes from 0 to square root of x. Then we have the integral over the thetas. I'm not even going to write them down. We will have, now we have an e to the negative r squared over 2, r to the n minus 1, g of theta 1 through theta n minus 1, dr to d theta n minus 1. So this is going to be 2 pi to the negative n halves, integral r goes from 0 to square root of x, e to the negative r squared over 2, r to the n minus 1, dr, times the theta crap. Okay? What does that theta crap integrate to? It doesn't really matter. It's some constant, but we actually know what constant it is. Think geometrically. I'm sorry?
Something that's related.
It's something related to the volume, but not the volume. You're close. Not the volume. One lower dimension. The surface area. Right? We're keeping the radius fixed, and then we integrate over. That's going to give you the surface area. So I'll just call it, Sn 2 pi to the negative n halves. And now, here's my function. I integrate it. So let's call this maybe f of square root of big H of square root of x, where h of r is e to the minus r squared over 2, r to the n minus 1. Could I do this? Probably. Do I need to? No! Why don't I need to integrate this? As much as I love integrating. Yeah, I'm going to take the derivative the next moment. Right? I'm going to integrate this, evaluate its square root of x, and then take the derivative. So there's no need to write down the antiderivative. So I get my density function at x is going to be Sn 2 pi to the negative n halves. Then I'm going to get the derivative of h, which is just my little function, h evaluated square root of x, times the derivative of square root of x. And so sadly, we just ran out of board space. Oh well. So we'll move back over here. We'll do a little bit of erasing. And so now when we substitute, we get fx of x is going to be Sn over 2 pi to the n halves. H of square root of x will become e to the negative x over 2. Oh, isn't that nice? Right? And now you can see why we have these factors of 2. Because the Gaussian, the standard normal, is negative x squared over 2. That's why we have to have the over 2 in the definition of the chi-squared variables. It's going to work out nicely over here. Then we have r to the n halves, but r is going to be square root of x. So we get x to the n minus 1 over 2. And then we have the derivative of the square root of x, which will become 1/2 x to the minus a half. And so when the dust settles, we get Sn over 2 times 2 pi to the n halves, x to the n halves minus a half, so it's x to the n halves minus 1, e to the negative x over 2. And this is a chi-squared with n degrees of freedom. And that's the proof. And in fact, you can now use the fact that this integrates to 1 to figure out what this normalization constant is. And that will get you the surface area. And if you wanted to get the volume, you can get the volume by integrating the surface area. So I'll make one or two quick comments on that once I'm convinced that everybody is happy with where we are here. In terms of using things, you just need to know the results. But in terms of if you want to go forward in the theory, it's nice to see how do you actually get these. These are painful calculations. Right? If you enjoyed Calc 3 where you're doing all these change of variables, have fun. Go online and look at what the generalized spherical coordinates are. Write down what the volume element is. Calculate the Jacobian if you even remember what the Jacobian is. If not, learn what the Jacobian is and then calculate what the Jacobian is. It's not fun. This bypasses all of that. And for free, you get the volume and the surface area of the n-dimensional sphere. Amazing. If this doesn't excite you about pure mathematics, then I'm done. I can't do anything else. And I will give up on trying to do that for the rest of the semester. Right. Any questions about the argument? Right. So then just as an aside, I just want to quickly remark on some things you may have seen before. So let's start off with the circle. And a sphere. So the area is pi r squared. The volume is 4/3 pi r cubed. The perimeter is 2 pi r, and the surface area is 4 pi r squared. And what you should notice is you're taking the derivative. So the question is, why is this true? Well, if you think about having a sphere, or having a circle, let's say of radius r, and then you increase the length of the circle by delta r, and you look at, well, what is the area of that annular ring? That's going to be pi r plus delta r squared minus pi r squared. And then this annular ring is approximately the perimeter of the circle times the thickness. So this is going to be approximately the perimeter at radius r times the thickness, which is delta r. And over here, to first order, this is going to be 2 pi r delta r. So you get that this is approximately equal to 2 pi r delta r. And this is how you can justify, if you know the area of the circle, this is what the perimeter is. You can play the same game with the volume of the sphere. If you expand the sphere ever so slightly, that's what you'll get. Okay. Any questions on this? So again, we now have a lot of powerful techniques. The theory of normalization constants is phenomenal in terms of what it allows you to bypass. All right, this is a good place to stop.